JWST finding the first stars in the universe? What's up with that? Let's back up a bit. Our star, the Sun, has mostly hydrogen and helium, whose origins we trace to the Big Bang itself. Well, how about all the other ingredients? Well, that would include carbon and nitrogen and oxygen and silicon and iron and dozens of other elements that were not there at the Big Bang. They had to come from somewhere, and we know where they came from. They came from stars, early stars that manufactured them in their core through thermonuclear fusion. This population of stars, such as our Sun, that is capable of making planets, has an age of about 5 billion years. The universe is about 14 billion years old. So we came pretty late. You know, the universe was already sort of 2/3 old before our solar system came on the scene. Because of the history of this exercise, we labeled our generation of stars, such as the Sun that made our planets, we labeled that population 1. Then we asked, surely a generation of stars before that would have fewer heavy elements in them, because heavy elements is something that continues to build over time. So the hunt was on to find stars of lower abundance of heavy elements than that of the Sun. And we found them. They live mostly in the halo of the Milky Way. This is a part of the Milky Way that our models for its formation tell us probably formed first. So we came to call those population 2 stars. These have a fraction of the heavy elements that the Sun does. 1/100th. We don't expect those stars to have vibrant planetary systems in orbit around them. The amount of ingredients available to them to accomplish this was low enough so we say, that's not a good place to look for planets. Population 2, we say, wait a minute, they can't be the first stars. If they too have heavy elements, however low that amount is. 1/100th of our heavy elements, 1/10, 100th, even 1,000th, is still more than 0. So they can't actually have been the very first stars. So thus was birthed the hunt for the first stars. These would have no heavy elements at all. They would just be hydrogen and helium with no prior generation of stars having contaminated their birth cloud to give them chemical ingredients other than those two, the ones the universe was born with. So we go from our population 1 to population 2. What are we going to call these? Population 3. So I'm apologizing for my entire field of astrophysics that these are numbered in reverse time order. By the way, if a star is born today, it'll have much more heavy elements than our Sun did, having been born 5 billion years ago. We might call those population 0. Point is, anything from Pop 1 onward is our best bet in our search for life in the universe, because all the heavy element ingredients are there. All right, so the James Webb Space Telescope that is exquisitely tuned to observe the birth of galaxies found evidence for the mythical population 3 stars. It has found light from a galaxy that has been observed through its spectra. Spectra is the way to know what elements lurk in the atmospheres of stars that are there. That's how you find out. When we look at a spectrum of the Sun, there's the fingerprint of carbon and nitrogen and silicon and sodium, and we have all of this in the Sun. Let's do this with other stars. You go to this early galaxy and there's no sign of any heavy elements at all. The best evidence yet for that mythical population 3 star that is made of just the ingredients of the Big Bang itself. Now, there's a side story here that blends into what I just said. Out of any family of stars just born, you can ask, well, how many stars of low mass are there? How many stars are of middle mass? How many stars are of high mass? everywhere we've ever looked, there are many, many more low-mass stars than high-mass stars. Okay, that's fact number one. Fact number two, the highest mass stars will burn out in a few 100,000, at most 1 million years or so. The low-mass stars can go trillions of years, longer than the current age of the universe. They get very good gas mileage, if you want to think about it that way. So, if the first generation of stars made stars like anybody else did later, with many low-mass stars and only a few high-mass stars, then we would see low-mass stars living today, lurking among us, that have zero heavy elements in them. And we don't. That forces us to conclude that whatever process that was making stars for the first time did not favor low-mass stars. We would still see them today. And it makes only high-mass stars. And that's the subtext of this story. Everything we understand about stars, their birth, stellar evolution, and their death, tells us that there's a limit to how much gas can accrete onto a thing that would become a star. There's a limit. And that limit is set by what we call radiation pressure. And as the star turns on, you have light, energy, trying to get out of the star. And if you have heavier elements there, they can resist the flow of that energy to exit the star. And it effectively creates a pressure on new coming gases that want to descend onto all the action. And so the formation of a star is self-limiting in its upper mass that it could achieve. However, if you're a pop 3 star and you don't have heavy elements, there's nothing to push against. And your luminosity could get really, really high, and your mass could just keep getting bigger and bigger and bigger. Some models allow hundreds of times the mass of the sun, and in some limiting cases, 1,000 times the mass of the sun. Whereas traditional models of forming high-mass stars, they top out at 50, 60, at most 100. And so pop 3 stars would be a different species of star for these reasons. These new stars would be copious emitters of ultraviolet light. This is high-energy light. But the James Webb Space Telescope is tuned to see infrared light. So why are they seeing these galaxies at all? Because since 13 billion years ago, the universe has expanded and the wavelength of ultraviolet light has been stretched to become longer and longer and longer, and it is now at our epoch arriving as infrared light. So the James Webb Space Telescope has built into its very design the ability to see high-energy ultraviolet light from the early universe as it arrives today in the infrared band of the spectrum. Not only that, galaxies that far away, that long ago, would be very hard to detect just by sheer distance alone. But there's a cluster of galaxies sitting between us and that target. Cluster of galaxies has a lot of gravity. Where you have a lot of gravity, you have what Einstein called gravitational lenses. Depending on the configuration of galaxies in the midground, light coming from behind it can be focused. Light coming in one direction will curve left, the other direction it can curve right, and the image of the galaxy you see can be a magnified version of that galaxy that would otherwise go undetected behind this gathering of funhouse mirrors that we call a galaxy cluster. So, it is gravitational lensing that allows us to detect this thing at all. It's the fact that it's giving off ultraviolet that allows the James Webb Space Telescope to see it at all. And it's the fact that we don't see any fingerprints of heavy elements that empowers us to declare that maybe we have discovered the first stars of the universe. What are the uncertainties? Any good scientific reporting talks about uncertainties. Maybe there's a gas cloud that's in the way that is masquerading as a star that has no heavy elements. All the telescope observation catches is light from this distant object. And you can presume that this light is the summed light of its stars, but it could be gas clouds that are in the way. And it's easier to think of how you can just have a gas cloud that has no heavy elements that just came right out of the Big Bang, so left over from the Big Bang. So it remains to be confirmed, but if it is, as all good scientific results need to be done before they become part of what is objectively true in the world, if it is confirmed, it'll be the first evidence of the first stars in the universe. So this result, which was just published in the Astrophysical Journal Letters by 3 colleagues of mine, Visbal, Hazlitt, and Bryan, 2 from the University of Toledo, 1 from Columbia University up the street here. So this is their efforts to try to look at the data coming to us from the early universe and try to make sense of what's going on there. This has been a What's Up With That? Neil deGrasse Tyson here, as always, bidding you to keep looking up.
James Webb Space Telescope researchers think they've spotted what could be the universe's earliest generation of stars, the elusive Population 3 era. It's a finding that could reshape how we think about the first chapter of cosmic history. But as usual, the moment science hits the news cycle, coverage splits. Different outlets emphasize different angles, and the gap between celebrating discovery and fueling speculation gets wider. So, who do you trust to give you the full picture?